All right, everybody. We are in chapter 4.3, section 4.3. We are going to be doing applications of systems of linear equations. What this is just the application problems from 4.2. We're going to be doing application problems just like we did in section 4.1, but we're going to be doing this in more variables. So the first thing we are going to look at is we're going to look at this example 1. You can find this on page 293 in your textbook. It's a blending problem, which means we're going to take some things and blend them together to make different things. All right, so the Arctic Juice Company makes 3 juice blends. Pine orange using 2 quarts of pineapple juice and 2 quarts of orange juice per gallon. Pine kiwi using 3 quarts of pineapple juice and 1 quart of kiwi juice per gallon, and orange kiwi using 3 quarts of orange juice and 1 quart of kiwi juice per gallon. Each day, the company has 800 quarts of pineapple juice, 650 quarts of orange juice, and 350 quarts of kiwi juice available. So this is the most important question right here, most important part of it. All right. How many gallons of each blend should it make each day if it wants to use up all the supplies? All right. So the very first thing we need to do is we have to define our variables. So what is X going to represent? X is going to represent the gallons of pine orange. Okay, Y is going to represent the gallons of pine kiwi. They really helped us out with these names because we know exactly what's in them. All right. And then Z is the gallons of orange kiwi. Okay, so once we have our 3 unknowns in this case, because we have 3 different juices that we're making, we have to come up with our equations that match this situation. All right, so we have 3 different types of juices that are made up of 3 different ingredients. All right, we have pineapple juice, kiwi juice, and orange juice. What we do know is that there's a limit on each of these 3 different things that are mixed up. Okay, we have 800 quarts of pineapple juice. 800 quarts of pineapple juice. So what uses pineapple juice? All right. So X, pine orange, uses pineapple juice. How many quarts of pineapple juice are in pine orange? That would be 2 per gallon. Okay. Now, how many quarts are used in pine kiwi? Well, we have 3 quarts are used in pine kiwi. And then we have how many quarts are used in orange kiwi? There are 0 quarts of pineapple juice used in orange kiwi. So we're going to represent that with 0Z. Okay. And that would be the 800 total quarts of pineapple juice that we have. So this first equation is just on pineapple juice. We're going to do the same thing for orange juice. Okay. How many quarts of orange juice go in pine orange? 2. How many quarts of orange juice go in pine kiwi? None. How many quarts of orange juice go into orange kiwi? 3. So that would be 3Z. How many quarts total do we have of orange juice to use? 650 quarts. Okay. Our last equation is going to represent the kiwi juice that we have. So how many quarts are used in pine orange? 0. No kiwi juice is used in pine orange. How many quarts of kiwi juice are used in pine kiwi? Just 1 quart per gallon. And then how many quarts are used in orange kiwi? That would be 1 quart per gallon. See, I messed up here, right? I wrote an X. I need to write the Y there because I'm talking about pine kiwi for that one. All right. And then how many total quarts do I have to use? I have 350 total quarts of that. All right. So that is the hardest part of these problems, I believe, is coming up with those equations that match this. What you want is if you have 3 variables, 3 unknowns, you want 3 equations. That's definitely something to keep in mind, okay? If you have 3 variables, you want 3 equations. All right, what we're going to do next is we are going to make an augmented matrix out of these. So what I'm going to do, just because I ran out of space here, is I'm going to get rid of my variables up here. And I'm going to write my augmented matrix, all right, out of this. So my augmented matrix is going to consist of 3 rows and 4 columns. So our 3 rows and 4 columns are going to be 2, 3, 0, 800, and then 2, 0, 3, 650, and then 0, 1, 1, 350. Okay. Now to solve that, what I'm going to do is I'm going to take my calculator. All right. Hopefully you can see this screen. When I turn it on, it looks good to me. All right. Is I'm going to enter that into my matrix, and I'm going to find the reduced row echelon form of that, like what I showed you in the 4-2 video. All right. If I go into my matrix menu, I want to edit a matrix. All right, I'm choosing to put it in matrix A. As you can see, I have 4 different matrices put in here, but I'm just going to overwrite A and I'm going to use it. This is a 3x4, so I'm going to enter in what I see: 2, 3, 0, 800, 2, 0, 3, 650, 0, 1, 1, 350. Okay. Now, once I have that stored in my calculator, I have to quit back out, and then I have to go back into the matrix menu, go to math, and all the way down to B, reduce row echelon form, and then I have to go back into my matrix menu and choose that matrix that I just input. So now I'm doing the reduce row echelon form of matrix A. And as you can see, I get a nice reduced row echelon form matrix. All right. And what does that mean? Let's figure that out. Sorry about all this erasing. All right. So hopefully you can see that matrix. All right. As you can see that we have that nice the ones going down diagonally. So what that means is that X equals 100, because that 1 in that first row is in the X column. So that 1X equals 100. And in the second row, that 1 is in the Y column. So 1Y equals 200. And then that 1 is in the Z column. So Z equals 150. Okay, we can look back into our variables that we defined, and what do these mean? Well, that means that we are going to have 100 gallons of pine orange. We are going to have 200 gallons of pine kiwi. And we are going to have 150 gallons of orange kiwi. Okay. that's based off of that and our defined variables. That combination will use up all of the chords that we have. Okay. Let's move on to our next problem. Our next problem, we are going to be doing example number 2 in that textbook. Okay. So example number 2, we're talking about purchasing aircrafts. All right. A new airline recently purchased a fleet of Airbus A330s, 300s, Boeing 767 300ERs, and Boeing Dreamliner 787-9s to meet an estimated demand of 5,400 seats. The A330-300 seat 330 passengers and cost $250 million each. The 767s seat 270 passengers and cost $200 million each, while the 787-9s seat 240 passengers and cost $250 million each. Okay, so what do we know about that? We know that how many of each type of aircraft did the company purchase? That's what we're trying to figure out. So we have to go through and we have to define our variables now. So what does X represent? What does Y represent? And what does Z represent? Okay, we're going to have 3 unknowns here. So the first one is going to be the number of, I will call this the A330s. Okay, you could write Airbus A330 300s if you want. I'm not going to waste my time there, right? Y is going to be the number of 767s, and then Z would be the number of 787s. Okay. So now, what do we know about each? All right. We know the capacity, so how many seats they have, and we know the price. We also know that this airline is trying to meet the demand of 5,400 seats, and it spent a total of $4,750 million on this. So it spent $4,750 million on these these airplanes. Okay. So our first equation is going to be on the capacity. So A330s, they hold 330 passengers each. So if we have 330 times X, that would be 330 passengers times the number of A330s that we have. And then 767s, they hold 270 passengers each. And then the 787-9s hold 240 passengers each. Okay, and that is going to bring us a total of, they want to carry 5,400 passengers at once in their fleet. Okay, and the next thing we're going to look at is we're going to look at the cost that we have. All right, we're going to do this in millions. The A330s they cost $250 million each. The 767s cost $200 million each. And the 787s cost $250 million each. And we spent they spent a total of $4,750 million. All right. So we have 3 variables and 2 equations. What we want is 3 variables and 3 equations. All right. The last equation is probably the toughest to figure out, because it says here in that second to last sentence, it says the total cost of the fleet, which had twice as many 787s as 767s. was 4,750. So that little fact there. So we have twice as many 787s as 767s. So we have to say, what one do we have more of? All right, we have twice as many 787s as 767s. Now, normally, you would look at this, twice as many 787s as 767s. You would multiply 787s by 2 to give you 767s, but that's incorrect. Okay, what we have to look at it as is we have to look at it as if we double the number of 767s we had, all right, that would produce twice as many and would be the total of the 787s. So we're actually looking at that Z would equal 2Y. So that's our third equation. But what I don't like about that third equation is it doesn't look like the other ones. What I have to do is I have to get it to look like the other ones. I need an X, I need a Y, and a Z on one side and an answer on the other. So what I can do is I can move the 2Y over. So I can actually take this and make it look like negative 2Y plus Z would equal 0. But I don't have an X, but I can easily add it in with a 0x. All right, so this is actually my third equation. Now, what is my augmented matrix going to look like of this? Now that I have 3 variables, 3 equations, what is it going to look like? Well, just take the coefficients of each. This is going to be another 3 by 4 matrix. Okay, hopefully you can see this. Hopefully I can write it all in this tiny space here. And we'll see what we have. All right, so we have 330, 270, 240 for our X, Y, and Z, and our answer would be 5,400. We have 250, 200, 250, and 4,750. And then our last and probably most confusing is 0, negative 2, Z, 0. Okay. So when we have that, what I'm going to do now, it's going to be kind of hard for me to do this. Hopefully I don't. There you go. That looks pretty good. Okay. If I go through and I enter this matrix in, right, once again, go to my matrix menu. I can choose any one that I want, but I have to edit it. And I'm going to choose matrix A again because it's already a 3 by 4 matrix. 3 by 4, and I just have to write over what's already there. Now to the next, 250, 200, 250, 4,750. Then 0, negative 2. Oh, that shouldn't be a Z. What should that be? That should be a 1. Sorry about that. And then 0. So what I want to do is I want to create a reduced row echelon form of that matrix. So once again, I have to quit out and then clear, then go back into my matrix menu again, go to math, go all the way down to B. And then I need to go back into my matrix menu and choose the matrix that I entered it in for. I've entered it in A, and I'm going to hit enter. Okay. And as you can see, I have the nice reduced row echelon form matrix right there. Let me just clear some space out so I can write it down for you and then interpret it. So the reduced row echelon form matrix is the 1, 0, 0, 5, 0, 1, 0, 5, and then didn't give myself enough space, 0, 0, 1, 10. Okay, what I like here is that nice 1 up and down. Okay, what does that mean? That means, hopefully that's not over everything. All right, what that means is we have x equaling 5, y equaling 5, and z equaling 10. Okay, what do these mean? If we go back to our defined variables, we have 5 Airbus A330s, we have 5 Boeing 767s, and we would have 10 Boeing 787s in our fleet. Okay, and that's what we're dealing with there. That's a nice problem. That's one of my favorites, one of the more challenging ones. I like that one. Okay. The last problem that we're going to deal with is we're going to deal with a traffic flow problem. This is a little challenging, all right, but it's pretty cool, all right. It's what a lot of municipalities use to figure out, kind of road studies. Civil engineers use this and things like that. You ever see the strips on the road and they're counting the number of cars? They're actually doing a problem very similar to this. All right, so traffic through downtown Urbanville flows through the one-way system shown in figure 8. I'm going to show it in the next slide. Traffic counting devices installed in the road, all right, shown as boxes. You'll see that on the diagram. All right, if you want to follow along, this is on page 295 in your book. All right, and so the traffic counting devices installed in the road count 200 cars entering town from the west each hour, 150 leaving town on the north each hour, and 50 leaving town on the south each hour. I'm going to concentrate a lot on A. I'm not really concerned about B, C, and D. Something that you can read in the book for that, but I'm going to concentrate on A. So from this information, is it possible to determine how many cars drive along Allen, Baker, and Cole Street every hour? We're going to do this by trying to figure out how many cars actually are on each of those streets in this hour and represent it with a system and things like that. So let's look at the diagram. Okay. As you can see, we have our roads conveniently labeled Allen, Baker, and Cole for A, B, and C. We're going to be we can use A, B, and C, or we can use X, Y, and Z. All right, let's define our variables right now. What are we going to do for our variables? We have X, Y, and Z. X is going to be cars per hour on Allen Street. Okay, and then we have cars per hour on Baker Street. And then we have cars per hour on Cole Street. Okay. So now we have to go in and we have to look at each intersection that we have. Okay. If we go back to our diagram, what we can realize here is that this first intersection tells us that if we add up the total of cars on Allen and Baker, it would equal 200. All right, so we have Allen and Baker equaling 200. How do we represent Allen and Baker equal 200? Well, that would be X plus Y would be our 200 cars. Okay, so when the 200 cars enter, they could either go to X or Y. Okay, if we go look at our next intersection, we go back and look at our next intersection. So I'm going to look at this intersection up here. What we know is that we have cars going to Allen, and then Allen, cars can either go to this 150 or down to Cole. So if we take the amount of cars that are in Allen and subtract the number of cars that go to Cole, we would be left with 150 So our equation would be that Allen minus Cole would be the 150 cars. Okay, so we have Allen and then the people that go off onto Cole equal the 150 people that end up and 150 cars that end up on the north end. Okay, go back to our equation and we have one more intersection to look at. What this is this car, these are cars that go down Baker and Cole, exit out to 50. So if we add up the number of cars on Baker, sorry about that, we add up the number of cars that are on Baker and Cole, they flow down this street and equal 50 on that south end. So we would have Baker, which is Y, plus Cole, Z, would equal the 50 cars. All right. What we notice here is that we do have three equations and we have three variables, but what we do not have is we do not have three variables in one equation. So I have to rewrite them that way before I write my augmented matrix. All right. So I am missing a Z in my first. So I can write that as X plus Y plus 0Z equals 200. In my next equation, I am missing a Y. So I can say 0Y minus Z equals 150. And my last equation, I am missing an X. So 0X plus Y plus Z equals 50. So my augmented matrix would be 1, 1, 0, 200, 1, 0, negative 1, 150, and then 0, 1, 1, 50. Okay. Now I want to find a reduced row echelon form of that. So I go to my calculator, turn it on, and I'm going to enter in a 3x4 matrix again. This one's pretty easy to enter in. Now I want to find my reduced row echelon form of that. And as you can see, I have something interesting happening. Okay. What I have is I have 1, 0, negative 1, 150. I have 0, 1, 1, 50. Then I have 0, 0, 0, 0. Okay. So what does that tell you, right? If I have a row of all zeros on the bottom and I have three variables and three equations, that zero is telling me that I don't have one exact combination. Okay. But what this does tell me is that if I know a particular number of cars that go down a street per hour, I could determine the number of cars, an equation to figure out the number of the cars that are on the other one. So my actual equation, it says, from this information, is it possible to determine how many cars drive along Allen, Baker, and Cole streets every hour? It is impossible to figure that out. All right. Because of all the zeros at the bottom. If I know one of them, I could find out the other two, but I cannot figure it out just by looking at the number of cars that go north and south. There's too many different combinations of that. All right. Thank you very much.